All right, today we are looking at solving linear systems now by the elimination method, also called linear combinations. Starting out this warm-up, we are just going to determine the additive inverse of these terms, which is going to be useful when we start using the elimination method. So the additive inverse of 4 would just be negative 4, of x would be negative x, of 20x would be negative 20x, the additive inverse of negative 9x would be positive 9x, and then the additive inverse of 78.5x would be negative 78.5x. All right, so moving on to the next page on this getting started activity, it says there are a total of 324 people who joined the Comic Gurus group on social media site. Female group members outnumber males by 34. Okay, so they say use reasoning to determine the number of males and females who join Comic Gurus. So to do this, we would basically be kind of testing numbers out to see if they work, picking out a number of females, number of males, seeing what the difference is, seeing if they add together to be 324. That can be difficult, can be time consuming. It's more of a guess and check method. So what we're going to be using is we're going to take that same situation down here in activity 3.1, and we're going to actually solve it algebraically. So we're going to write the system that represents that problem situation, use X to represent female members of the group and Y to represent the number of male members in the group. So the first equation says there's a total of 324 members, so we could say X plus Y equals 324. And then the second equation says that females, which is X, outnumber males by 34. So females minus males would equal 34. So there's our system of equations that we could use to solve that. Now using that, if we move on to the next page, it shows how Chloe used substitution method to solve this. What she did is she solved one of the equations for one of the variables, solved it for X, and then substituted in Y plus 34 for that X. And she got a solution of 145 for Y and 179 for X. Mara used the method we're going to talk about today, elimination. Essentially adding the two equations together once they're aligned in standard form and using the additive inverses to eliminate a variable. So in this case, Y plus negative Y, once the equations are aligned, are additive inverses and cancel out, leaves her with just the X variable, where she could solve for X and then plug it back in to find the Y value. So explain why each student is correct. Well, they're both correct. Chloe just used substitution. And Mara used elimination or linear combinations. I'm going to call it elimination. So remember, all these methods are just different methods to be able to solve the same problem. Sometimes a certain method sets up better given the situation to use that method. So it says examine the structure of the system. What characteristics of the system made Mara's strategy efficient? Well, they were aligned, variables were aligned. In standard form. And there was already additive inverses in one of the coefficients. So the Y's already had additive inverses of 1 and negative 1. So the solution to their system, they both got the same solution, which was 179 for X, 145 for Y, which was 179 females and 145 males. Okay, on the next page, it says the algebraic method used by Mara to solve the linear system is called linear combinations. Okay, I often call it elimination because we're eliminating a variable. The linear combinations method is a process used to solve a system of equations by adding two equations together, resulting in an equation with one variable. You can then determine the value of that variable and use it to determine the value of the other variable. So once we find the first variable, we can plug it back in, find the second one. So it says to solve each system of equations using linear combinations. So both of these are set up already where everything's aligned and we already have additive inverses. So for the first one, what variable is going to cancel is our y, and then we add straight down. Negative 4x and negative 2x add to be negative 6x. 10 plus negative 1 is 9. And then we divide by negative 6. And we're going to get x equals negative 1.5. Okay, from there, we go plug it back in. Now, again, either equation works to plug it in. I look for certain things. Like if I'm solving for y, I'm going to choose that equation that already has plus 1y. It's going to be shorter to solve it. So negative 4 times x, which is now we know is negative 1.5, plus y equals 10. So negative 4 times negative 1.5, when we multiply that, gives you 6. And then we can subtract 6, and we get y equals 4. So my solution there is negative 1.5 for x, 4 for y. And then the second one, we got the x's are already aligned in additive inverses, negative 1/2 and positive 1/2. So those will cancel. 5y plus 1y is 6y. Negative 6 plus negative 6 is negative 12. So then we can divide by 6, and that gives us our y value is negative 2. Now, if we plug that back in, again, when I look at these two equations, I'm probably going to pick that second one, just plus 1y to plug that in. So I have 1/2 x plus 1y, or we could just say minus, let me erase that, minus 2 instead of plus negative 2, which I was about to write, equals negative 6. And then we can solve for x now. So plus 2 gives me negative 4, and then multiply by the reciprocal to cancel out that 1 over 2. And we get x equals negative 4 times 2 is negative 8. So that solution is negative 8 for x, negative 2 for y. So both of those, we use linear combinations that were set up perfectly to use it with additive inverses. Okay, and the next activity, using additive inverses to combine linear equations. Now you notice in this worked example they have here, everything is aligned in standard form, but we don't have an additive inverse. So we got to create one. So if we're looking at that equation, there's nothing I can multiply 4 by to get 7. So I'm going to look at the y's. So if I have 2y in that first equation, I need negative 2y in the second equation to create that additive inverse. So we can multiply that equation by negative 2, which is exactly what they show here. Once we multiply by negative 2, now it's just like the first two we worked. We got that pair that cancel, and as long as we multiply the whole equation by that number, it creates an equivalent equation, which allows us to do that. So once we get that additive inverse pair, then everything proceeds just like we did on the previous examples. So it says in that worked example, only one equation needs to be written to solve the linear combinations y, and that's simply because we can multiply one equation and create additive inverses. So we want to be able to do as little work as possible. So if we can just multiply one equation, we want to do that. Now we're going to see some where we have to multiply 2, but if we can only get away with multiplying 1, that's the best scenario. Okay, so now let's consider this system of equations where both equations need to be written. Now the reason they both need to be rewritten is there's nothing I can multiply 4 by to make it equal to 5 for the x, and there's nothing I can multiply 2 by to make it equal to 3 for the y. So we're going to have to pick one of the variables and change it. You could work with either one here. When I have to choose, I pick the ones that have the smaller numbers, so 2 and 3. So basically, we're going to multiply each of them by the additive inverse. So I'm going to multiply the 2 by 3, that equation, and I'm going to multiply the equation with a 3y by negative 2. And you could have done the signs opposite. You could have multiplied the first one by negative 3 and the second one by positive 2. As long as we end up where one of them's positive and one of them's negative, that's what we need. Okay, but again, the goal there is just to create that additive inverse where we have a pair that cancels. Okay, just be careful of your signs. If you accidentally multiply, don't change your signs. You might look like you have a pair, but they might be the same sign. We need them to be inverses of each other. Okay, so it wants us to determine the solution for the linear system that they showed in the second worked example. So in the second worked example, they have now changed. rewrite this. 12x, get my pen to work, plus 6y equals 9, and negative 10x minus 6y equals negative 8. So our y's cancel. That leaves you with 2x equals, is it negative 8? Yes. 9 minus 8, so 1, and then divide by 2. So we get x equals 1/2. And again, we can go plug that back in. Now, when you plug it back in, you can plug it into the new equations you created by multiplying them, or you can go back to the original equation. Excuse me. I often go back to the original equations because you're usually dealing with smaller numbers. So I'm going to go back and use that 4x plus 2y equals 3. So 4 times x, which I now know is 1/2, plus 2y equals 3. So 4 times 1/2 is 2. Then I'm going to subtract 2. I'm going to move down here for some more space. So 2y equals 3 minus 2 is 1, and then divide by 2. So our y is also 1/2. So our solution is 1/2 for x, 1/2 for y. Okay, how could we have solved this system by creating the x values? So if we go back to those x values, you could have done that by just multiplying, say, this one by negative 5 and this one by 4. We'd have found the same solution. We would have just found the y value first that time because we'd have been able to cancel out the x's. Either one is correct. So in question 4 now here, it just says describe the first step we would need to solve each of these equations. So looking at A, we have a pair. They're both 2's with the y's. They're just the same sign. So we could start by just multiplying this one by negative 1. And now we would have, this would be changed to our new equation, and now we have that linear pair. So for B, for this one, the easiest method by just multiplying one equation would be the x. If the second one's 5x, we can multiply by negative 5 and make that negative 5x minus 15y equals negative 75. And now we would have an x value that cancels. Okay, and then C, now this one, we run into a problem. We got to multiply both equations because for the x's, there's nothing I can multiply 3 to get 4. For the y's, there's nothing I can multiply 2 by to get 3. So I'm going to work with the smaller numbers, the 2 and the 3 with the y. And I'm going to multiply the top one by negative 2 and the bottom one by positive 3. That way we're going to end up with negative 6y and positive 6y. Just make sure you multiply everything in the equation by that term. So we're going to have negative 8x minus 6y equals negative 24 for the first equation. And for the second equation, we'd end up with 9x plus 6y equals 12. So now we have that vertical pair that's additive inverses that will cancel each other out. Okay, so same thing again. We're going to look at how we could cancel out a vertical pair with these. So just like we were doing on those other examples. So for A, I wouldn't change anything. We already have a vertical pair, 1/2 x, negative 1/2 x. So I would just say I would not change. Now, here in a minute, we'll look at how we can eliminate fractions if we don't want to deal with the fractions. But since that pair already cancels, I probably wouldn't change it. For B, I'd work with the y's because for the x's, nothing multiplied by 3 gives me 4, but I can multiply that equation by negative 3, and I would now cancel out my y's. So I'd have 4x plus 3y equals 24, that first equation unchanged, and then negative 9x minus 3y equals 6. So 4x minus 9 would give you negative 5, and then you'd add 24 and 6 and get 30. So again, as long as we're just finding that first step to make where we have the pair that cancels. Very similar with C. Gonna have to multiply both equations, so I'd probably pick the smaller numbers, which are with the x's. So I'd multiply that first equation maybe by negative 2, second one by 3. Again, you could have multiplied by positive 2 and negative 3. As long as we get the opposite signs, we are good. So that first equation would become negative 6x minus 10y equals negative 34. And the second equation would become positive 6x plus 3 times 3 is 9y equals 33. And there we would have our vertical pair that cancels. Now the next two are going to be a little unique. It's going to go back to what we talked about in our last lesson about no solution and infinite solutions. So on D, I'm going to try to eliminate y. So if we got 3y, I'm going to make the second equation be negative 3y by multiplying by negative 3. So if I rewrite the first equation, second equation would have negative 6x minus 3y equals negative 3. And what we're going to see now is now both variables are inverses. So if those were to both cancel, we'd be left with 0 equals 2, 5 plus negative 3. Well, that's not a true statement. So what we talked about in previous lesson, if we end up with the variables cancel each other out, if we have a false statement, that means there is no solution. And then E is going to be the opposite. We're going to multiply, let's say, by negative 2 to cancel out the x's. So then I get negative 2x minus 4y equals positive 12. Now what happens here, not only do our variables cancel, but negative 12 plus 12 cancels. So we end up with 0 equals 0. So if we end up with a variables canceling each other out, but the statement we're left with is mathematically true, now this is when there is infinite solutions. All right, so now that we've been through the method and all the different scenarios you might come across, we're going to look at now applying that. So this question says, Let It Snow Resort offers 2 winter specials, the Getaway Special and the Extended Stay Special. The Getaway Special offers 2 nights of lodging and 4 meals for $270. The Extended Stay Special offers 3 nights of lodging and 8 meals for $435. So we're going to write a system of equations. Let n represent the cost for 1 night of lodging and m represent the cost of each meal. So our first equation for the first situation was 2 nights lodging plus 4 meals equaled $270. Okay, the second equation was 3 nights lodging plus 8 meals for $435. So there's our 2 equations. So how are these equations the same? Well, they're both in standard form. But how are they different? We have no additive inverse pairs. With either of our variables. All right, so it wants us to now solve that system. So I'm going to go down here. I'm going to rewrite it. 2n plus 4m equals 270, and 3n plus 8m equals 435. Okay, so looking at that, I would have to multiply both equations to cancel out the n. So I'm going to multiply this first equation by negative 2 to cancel out the m. So that's going to give me negative 4n minus 8m equals 270 times negative 2 would give you negative 540. So now we got what we need, a vertical pair that cancels. 3n and negative 4n give me negative 1n when I add those together. And 435 plus negative 540 gives you negative 105. So last, we need n to be positive. So if we divide by negative 1, or if you think of negative n equals negative 105, positive n would equal positive 105. Now we can go plug that back in and solve for our missing variable. So if we now know that n is 105, I'm going to use the very first equation, this one here. So 2 times 105 plus 4m equals 270. So 2 times 105 would be 210. I'm going to subtract 210 and move that to the right side. So now I have 4m equals 60 and then divide by 4. So m equals 15. So the cost of a meal would be $15. The cost per night is $105. Okay, which is what we're going to answer on the very top of the next page when we interpret that solution. So all that solution means is cost per night was 105, and our cost per meal was $15. Okay, check your solution algebraically. We just did by solving it. If you wanted to go plug back in the n and the m and make sure it satisfies both equations, you could, but we've got our solution by solving it algebraically, so we are good. Okay, so is the extended stay special the better deal? Okay, well, it just depends on really where you want, what's your priority. Do you want to stay a longer amount of time, have more meals? So that's going to be a personal choice just depending on each situation. Let It Snow Resort charges the same amount for meals and lodging, so really it just comes down to how long do you want to stay. Neither one is giving you a better price break since the variables satisfy both situations. All right, fractions and linear combinations. So it says the school spirit club is making beaded friendship bracelets with the school colors to sell in the school store. The bracelets are black and orange and come in 2 lengths, 5 inches and 7 inches. The club has enough beads for a total of 84 bracelets. So far, they have made 49 bracelets, which represents 1/2 of the 5-inch bracelets and 3/4 of the 7-inch bracelets they plan to make and sell. So we're going to determine how many of each length bracelet they plan to make. So it says let X represent the number of 5-inch bracelets and let Y represent the number of 7-inch bracelets. Okay, well, one equation we could write is just the total bracelets they want to make. X plus Y equals 84. Second equation is going to be a little uglier. We've got some fractions to work with. So 1/2 X plus 3/4 the number of Y bracelets they want to make currently equals the amount they've made, which is 49. Now, for 2, it says Karen says that the first step to solve the system is to multiply the second equation by the least common denominator of the fractions. Jacob says the first step is to multiply the first equation by negative 1/2. Who's correct? Well, really, they're both, either one would work. If we multiply the first one by negative 1/2, the x's would cancel by additive inverses. What Karen's trying to do is eliminate having to work with the fractions, which can make it much easier. So we're going to rewrite that equation on the top of the next page, and we're going to talk about how we can eliminate those fractions. All right, so if we follow Karen's method by multiplying the second equation by the least common denominator, for instance, if we wanted to multiply by 4, we're going to pick that larger denominator. What that would change, 4 times 1 is 4, so 4 divided by 2, 4 times 1/2 is 2. For 5 times 3/4, 4 times 3 is 12, divided by 4 is 3. And then 4 times 49 is going to give you 196. Well, now we've changed that equation and we have eliminated the fractions. So if we now line them up, we can solve them using elimination without having to worry about the fractions. So now we could look at perhaps eliminating the x by multiplying the first equation by negative 2. So that'd become negative 2x minus 2y equals negative 84 times negative 2 would be negative 168. So now our x's cancel. 3 minus 2 is 1. 196 minus 168 is 28. So we know y, the number of 7-inch bracelets, is 28. And if we go plug that back in, x plus 28, using this first equation here, equals 84, we can solve for x. We can subtract 28, and we're going to get x is equal to 56. So there's 56 5-inch bracelets, 28 7-inch bracelets. So we have 56 5-inch bracelets and 28 7-inch bracelets would be the meaning of our solution there. All right, so to wrap up, it says describe how each method and the characteristics of the system make this method the most appropriate. So like I mentioned earlier, we're just using different methods to solve differently systems of elimination, and it comes down to how is it set up best, which method works best. So typically graphing is only going to work best if the solution is an ordered pair of integers, where they're going to cross directly at one of those grid line intersections. Because if it doesn't cross perfectly at one of the grid line intersections, then we're essentially estimating what our solution is, because we can't exactly tell what that fraction or decimal is that is the x or y value. Okay, when does substitution work best? Substitution works best when one equation has a variable isolated. So in other words, if one of the equations is like y equals x plus 2, well, we could easily now take x plus 2 and plug it in, substitute it for the y in the other equation. So as long as one of the equations is set up like that, substitution is probably the best method or easiest method to use. And then when does linear combinations method work best? It's going to work best when both equations are in standard form. Then linear combinations would likely be your best bet to solve that